somewhere on your collar.
Yeah.
You can do this in your pocket or on your belt or whatever you want.
Okay. Do I need to? It's already on, right?
Yeah. Pleased to have here Simone Giombi telling us about higher-speed theories and ADS.
Okay, thank you very much. Let me first thank the organizers for the opportunity to give these lectures here. It's a really nice school and nice place, my first time here. So in these lectures, I will try to give an introduction to theories of gravitational theories involving higher spin fields, and in particular, trying to explain some recent progress in understanding their role in the ADS-CFT correspondence. So, as I said, the theories that I'm going to discuss are theories of gravity plus massless higher spin fields. And these theories will be defined in ADS, as we will see. And the important point I'm stressing here is that I want to discuss theories of massless higher spin fields. Of course, we could talk about massive higher spin fields, but that's not the focus of these lectures. Okay, and by higher spins, of course, I mean spin greater than 2. Okay, that's what higher spin means. So the familiar lower spin fields, spin 0, half, 1, 3/2, and 2 are those that you are all familiar with, and by higher spin here I mean something more exotic, spins greater than 2. Okay. So the problem of writing down consistent theories of fields of higher spins is a very old problem. It dates back to the beginning of quantum field theory. It was understood very early on that, at least theoretically, higher spin fields are possible from already in the 30s, from the work of Dirac, Wigner, Bargmann, and Wigner. It was clear that particles are classified by irreducible unitary representation of Poincare group, and there are representations of arbitrary spin. So at least at the free level, particles massive or massless of any spin are possible. The problem is whether it's possible to write down actual theories which describe consistent propagation and consistent interactions of these fields. Okay, so the simplest example of a spin S field in the usual language of relativistic field theory would be for me a field with S indices, totally symmetric, okay, so in the Young tableau notation, this will be a representation of the Lorentz group with S boxes, totally symmetric, and traceless. So this is the simplest example of spin S fields. One can consider more complicated so-called mixed symmetry higher spin fields, but I will not discuss those in these lectures. I will restrict to this the simplest example. Actually, if we are in 4-dimensional space-time, this is all we have. But if we are in higher dimensional spacetimes, we can have more complicated higher spin fields, which are labeled by more complicated representations of the Lorentz group. Okay? All right. So the problem, as I said, that I want to focus on is the problem of massless fields. And it's in this case that it's particularly hard to write down consistent theories for this kind of fields. And the reason is that these descriptions in terms of this field has a lot of redundancies. Because if we have a massless field, say in 4 dimension, we know just by representation theory, from Wigner, we know that it has 2 physical degrees of freedom, just plus S and minus S helicities, but this has many more. So associated to this field, there must be some kind of gauge symmetries to get rid of unphysical polarizations. Okay, so for massless fields, we must have gauge symmetries. Okay, so spin 1 and 2 are very familiar cases. If we have, let's say, the Maxwell field, there is a gauge symmetry, which is just the usual gauge symmetry with a spin 0 gauge parameter. For spin 2, let's say linearized gravity, then at the linearized level we have a gauge symmetry of this type with a spin 1 gauge parameter. So far, I want to first discuss propagation of free fields. So I'm just talking about linearized gauge symmetries here. I'm not including the nonlinear part of this transformation. So it's clear how to generalize this for general spin. For general spin, we must have some gauge symmetry with a spin s minus 1 gauge parameter. Is this too low? Appropriately symmetrized here. Okay, and the indices μ1, μs minus 1. Okay, so these gauge symmetries it's a large group of gauge symmetries, and they are very constraining, and they make very hard to write down consistent theories for these fields. Even at the free level, it's already a non-trivial problem to write down a consistent equation of motion which has this gauge symmetry. Okay. Any questions so far? Yes, I'll use this one. Okay. At the free level, the gauge invariant equation of motion and Lagrangian is known, is okay in flat space, in ADS or DS, and this was done by Fransdal in '78. We will review this a bit later. So, but at the free field level, it's indeed possible to write down a totally off-shell equation of motion in Lagrangian, which has this gauge symmetry, and which, when you go on shell, reproduces correctly the propagation of 2 degrees of freedom, which are the plus s and minus s helicities. But the real problems start when you want to write down interactions. Okay. So in flat space, there are actually powerful so-called no-go theorems that essentially forbid interactions of massless fields of spin greater than 2. Of course, we all know that we can write down interactions for spin 1 and spin 2 fields. It's just Yang-Mills and gravity. But if you try to go higher than that in flat space, then you encounter big trouble. And, well, 2 famous no-go theorems are the Weinberg low-energy theorem in 1964 and the Coleman-Mandula theorem in 1967. Essentially, so these are both S-matrix arguments, so they don't involve discussing any Lagrangian or equations of motion. They just involve studying properties of some S-matrix, assuming that the theory has some massless field of spin, say, greater than 2. And the problem is that due to the higher spin symmetries, then the S-matrix will have to have a symmetry, a conservation law of spin s minus 1, which turns out to be too constraining to allow any non-trivial S-matrix. So, for example, the Weinberg low-energy theorem starts by considering some general scattering process of particles 1 to n. This could be scalars or particles with spin, massive or massless, and then study the case in which there is a spin s massless field with momentum q, and looking at the limit in which q goes to 0. So that's why the name Weinberg low energy theorem. And I'm not going to discuss this in detail. You can read for example, a good introduction to this in Weinberg textbook. But what Weinberg see by studying this as matrix and taking the low energy limit for q going to 0 is that when this particle is massless, then there must be some conservation law which takes this form, summing over all the particles from 1 to n, gi, where gi is some coupling. This one will be gn. So each particle, I say, couples to the spin s field with a coupling gi, and then pi mu1, pi mu2, pi mu s minus 1 is equal to 0. So essentially adding this massless spin s particle implies that, well, by studying this S matrix and taking the q going to 0 limit, Weinberg derives this conservation law, which is a spin s minus 1 conservation law. You can see that the cases of spin 1 and spin 2 are essentially the familiar cases. For spin 1, this is just charge conservation. So in that case, GI would just be the electric charge of each of this particle. For spin 2, this would give a spin 1 conservation law of this type, which can only be solved for generic value of momenta, can only be solved if all the GIs are the same and the momentum is conserved. So this is just momentum conservation plus the fact that the graviton couples to all particles with the same strength. But for spin greater than 2, there is no non-trivial solution. So essentially, for spin greater than 2 for massless particle, the S matrix must be trivial. There is no interaction. Okay, so Coleman-Mandula theorem is a somewhat more abstract argument, but it's similar in the sense that the theorem says that if you have a general S matrix, it cannot have symmetry bigger than the direct product of Poincaré times an internal symmetry. But if you have particles of spin s, then you will have some conserved charge of spin s minus 1, which do not commute with Poincaré group, so they are not allowed by the Coleman-Mandula theorem. Okay, so essentially in flat space, if we want to describe interactions of massless spin s field, we run into great difficulty. Any questions so far? So given these no-go theorems, it came a little bit as a surprise that there was actually a yes-go result in the late 80s and early 90s by Fradkin and Vasiliev, and then mainly a series of papers by Vasiliev. So this is 87. And this is several papers in the early 90s. Okay, and the ESCO result is that they were able, so assuming a non-zero cosmological constant, which means that we are not studying flat space, but we have these particles in ADS or DS space, assuming non-zero cosmological constant, they were able to write down consistent, fully nonlinear equations of motion. Describing at fully nonlinear level interactions of fields, massless fields of any spin. There's some other one in the middle here. Okay, so we will later in the lecture write down what these equations of motion are in detail. But let me just summarize now some features of this theory. So I can write here. Which I will refer to as Vasiliev theory, because Vasiliev was the main guy involved in writing down these equations. Okay, so as I said, we have exact equations of motion. They are gauge invariant and fully consistent. Action is not well understood. But for many things that I will discuss, we would not actually need an action. Well, this is this one open problem, though there are some proposals, but it's not very clear at this point how useful they are for ADS CFT calculations, but maybe we'll come back to that later. So these theories exist in any D, in any dimension. In this lecture, we will focus mainly the case of dimension 4. Okay, so as we will see later when we write down these equations, by themselves they are background independent equations in the sense that they don't assume any background where these fields are propagating, just like Einstein gravity. You have some equations, then you can write down, you can find a solution and let things propagate on that background. So these equations, they don't assume a background to begin with, but you can show that they have a solution. So they are background independent, as I said. They have a vacuum solution, which is ADS or DS. So there are two versions of the theories depending on the sign of the cosmological constant. So they are complicated equations. They can have many solutions. We will see it's very easy to see that they have a simple solution, which is ADS space or DS space. And that's the vacuum in the sense that it's the most symmetric solution of these theories. So once you have identified this solution, you can study what is the spectrum that this theory gives you when you propagate fluctuations on this background. And the spectrum so the linearized spectrum in the case of ADS4 theory is the following. So there is a spin zero field which has some value of the mass which is fixed by the equations. It's not a free parameter, and this mass turns out to be -2 in units of the ADS radius. Okay, this you see a negative value here, but this in anti-de Sitter space, this is a perfectly unitary scalar field. Its mass is above the Brighton-Lohner-Friedman bound. So that's no problem with this sign. We will see later that this value of the mass is very natural from point of view of CFT. Okay. So that's scalar, and then there is a tower of massless fields of all integer spins up to infinity, massless. Okay, so this is what you get if you study those equations of motion at linearized level around the ADS background. And then if you go on in perturbation theory, you can read off what are the interactions between these fields. So the equations are fully nonlinear. You can solve them in perturbation theory and read off what are the interactions order by order. And because the equations are consistent and gauge invariant, you are guaranteed to get consistent interactions for all these fields. Okay, so one feature here is that they always include gravity. In the spectrum, there is always a graviton. So these are theories of gravity plus a tower of extra massless fields. By the way, so this is the simplest version of the theory. There are more complicated versions. So this, I would call this the Bosonic Vasiliev theory in ADS4. There are more complicated version of the theories in which you can also have half-integer spins, or you can have more fields of each spin. This is like the simplest version. But the common feature of all these theories is that there is always a graviton. Okay, there is no theory in which there is no graviton. Okay, so these are always theories of gravity. And another feature is that if you look at how the interactions between these fields look like, they always involve higher derivatives. So these are higher derivative theories of gravity. So at the free level, these are just standard two-derivative wave equations for these fields. Everything is standard, unitary propagation to derivatives, but interactions are higher derivative. So in particular, in the gravitational sector, it's not just Einstein gravity, but it's Einstein gravity plus higher derivative terms. And again, we'll see that this feature is very natural to understand from point of view of the CFT. Okay, we must have such a thing. Okay. And also another feature that I should stress, that it's already obvious here, is that the catch in the construction of these theories, to be able to write down consistent interactions of massless higher spin fields, you need to have an infinite tower of fields. Okay, so that they always involve infinite towers of fields. Okay. Now there are versions in lower dimensions in ADS3 where it's actually possible to truncate to a maximum spin. I'm not going to discuss those versions because they are somewhat different from what I will discuss in these lectures. But from 4 dimension and up, these theories always involve infinite towers of higher spin fields. Okay? All right. Okay, so as I said here, what we know so far is a set of equations of motion. So this is like a classical theory. But it's possible that because this theory has a large amount of symmetry, this higher spin symmetry, which is infinite dimensional because there are an infinite number of massless fields, it's possible that these theories can be quantized and they are well behaved at the quantum level. There may be interesting models of quantum gravity, which may be UV finite. This is speculation, but later in the lectures, I will show some partial evidence towards this. So as I said, the quantization of this theory is not fully understood, but at one loop level, it's not difficult to compute some one loop correction, for example, to vacuum energies in these theories. And an interesting thing that you can show is that one loop UV divergences actually vanish in these theories as a result of summing over this tower of massless fields. Okay, so that's, as I said, is speculation, but there is some partial evidence at one loop. Any questions before I go on?
Yeah. So
Yeah.
with higher derivative interactions,
Yeah.
the only reason they're allowed is
Sorry, I didn't catch the first part of the question.
derivative interactions.
Yeah.
Traditionally, you're not complete from themselves, so it's just one special property of only infinite power. The theory would be not the problems. Right, traditionally, higher derivative interactions don't cut off.
Right. No.
Cut off.
Yes. Now here. Yes, it must be related to the fact that there's an infinite tower of fields and you have some cancellations. It's important to. These are high derivative interactions, but there is no alpha prime. There is no truncation. There is all orders in these higher derivatives that you get in interactions. So it's a bit like string theory, but tuning alpha prime to 0. To infinity, sorry.
So what was wrong with the no-go theorem?
Well, those are in flat space. So here we assume non-zero cosmological constant, and there are no S-matrix. There are no S-matrix arguments. So the other thing to stress is that the lambda going to 0 limit is singular in these interactions. Okay, so there are higher derivative interaction, and there is always powers of 1 over lambda in front of them, and there is no well-defined flat space limit of these theories, which agrees with those no-go theories, because in flat space we don't have interactions of massless fields of spin greater than 2. Other question? Yeah.
Can you also consider ADS space with black hole?
That would be some. Well, you have to find out whether this theory has such a solution. Okay, so as I said, the equation of motion are background independent equations. You can study which solutions those equations support. ADS is the simplest one. You can ask whether there is a black hole solution, and then try to do perturbation theory around that solution. There are such solutions. There is a black hole solution that was found by Vasiliev and Didenko a few years ago. It's not been studied very much so far because it's hard, but there are such solutions are possible. Anything else? Yes. Right. So there is only ADS length, and then there is Newton constant, which doesn't appear in the equations of motion, but it would appear in the action, in front of the action. So there is only one dimensionless parameter, which is obtained by taking ratio of ADS length and Newton constant, so Planck length. And that would be related to n in the CFT. Okay. Anything else? Okay. Okay, so before actually going into the details of the construction of this theory, which we'll not do today, we'll do in the next lectures, I first want to discuss these theories from the point of view of ADS-CFT, looking at things from the CFT side. So I just want to argue that from ADS-CFT point of view, it's not surprising that such theories exist. Okay? It was surprising when Vasiliev constructed them, but if we think in terms of ADS-CFT, it's not too surprising that these theories must exist. Okay, so higher spins from CFT. Okay. So you already had 2 lectures about ADS CFT from Joao, and so not going to discuss too much about ADS CFT, but in the most general terms, ADS CFT is some correspondence between a theory of quantum gravity, let's say in ADS d+1, and some CFT at the boundary of ADS. So by this, I assume you've drawn similar pictures. So this disk is ADS, and the circumference is the boundary. Okay, just schematically. So if we accept this as some general correspondence between conformal field theories and quantum gravity in ADS, then we can see that it's not too difficult to find a CFT which has precisely the right features to be dual to theories of this type. Okay, it's actually a very simple CFT. It's a trivial CFT. So consider the following CFT: free, scalar, massless, of course. So let me write it down in dimension, general dimension D. And let me take, for now, a complex collection of complex scalar fields. So because in the end we will need some kind of large n limit, I take n of them, n massless scalar fields, complex. So, well, we will be mostly interested in the case in which D is equal to 3, so the CFT is in 3 dimensions and the higher spin theory is in ADS4. But what I'm saying here is completely general. I can phrase it in any D. Okay, so let's take the trivial CFT. So it has a UN global symmetry. Where this phi I is in the vector representation or fundamental representation. Okay. So this I will call a vector model because I take the matter in the vector representation. So this is probably a bit different from the type of theories that Joao focused on, which were probably theories with fields in the adjoint representations. So something like this. For example, theories like this, right? So I watched your lecture notes. So right. So this theory in which the field is is a single trace operator in some adjoint representation. What I want to focus on here is a vector model instead, and the reason will become clear soon. Okay. So I want to go to here. Okay, so once we have this very simple CFT, this free CFT, it's not difficult to see that this CFT has many conserved quantities, actually infinitely many conserved quantities. There is a tower of conserved operators of all spins. And of course, the lower spin operators are the familiar ones. For spin 1, we just have the usual spin 1 current. Right, which is a conserved operator, is a primary operator of the CFT with conformal dimension d minus 1, right? And then there is a spin 2. That's, of course, just the stress tensor. So this CFT admits a traceless conserved stress tensor. So this symbol will always mean symmetrization of the indices. Let me write it like this. So this would be the usual stress tensor, but then in a CFT, to make it traceless, we have this improvement term. So this operator is conserved and traceless, and it's traceless due to this additional term. These two terms are separately conserved, but to make it traceless, you have this extra term here. And well, one way to derive this stress tensor is to start with curved space, as you probably many of you know. So let me just open some parentheses here before I go to the higher spin operators. So you know that one way to derive stress tensor is to put the theory in a curved background. Yes. Yes, but okay, here I'm using the terminology vector model just to say that these fields are in the fundamental representation of SO2n, yes. Yeah. Well, the most the most common way to write this is in terms of real fields, then it's just ON and the vector representation. Here I'm writing it in terms of complex fields. Right. There is a difference. There is a difference between UN and SO2n that is not clear at this point yet. So at this level, it's the same. I could write this in SO2n basis, but later I will impose a truncation of this in the CFT. I'm not actually studying the full CFT, but just the singlet sector. And then it makes a difference whether you want to study UN singlet operators or SO2n singlet operators. Okay, so we'll see what is actually dual to the higher spin theory is the singlet sector of this CFT. And then there is a difference whether you impose UN singlet constraint or SO2n singlet constraint. Okay. Okay. So I was saying that one way to derive this improved stress tensor is just to start in curved space with a Weil invariant action, which involves coupling the scalar field to the Ricci scalar of the background in such a way that this action is Weil invariant, is invariant under rescaling of the metric. And then you can derive that stress tensor by the usual definition. This, where in the end you send the metric flat. Okay, so if you start with a Weil invariant theory in curved space, you're guaranteed to get a traceless stress tensor once you do this procedure. So as an exercise, if you've never seen this, you can try to derive this this term in the stress tensor by starting with this curved space action and trying to apply the definition. Okay. All right. So these are the spin 1 and spin 2. So this, of course, stress tensor is a conformal primary of dimension d. And then it's not difficult to go on and see that there are higher spin objects which have similar conservation properties. So I will write some object with S indices, J mu1, U2, mu S, and this will be similar to those, will be some bilinear in the scalar fields phi with S derivatives. And this expression is just schematic. So in the same way as you see in the stress tensor, these derivatives can be distributed among the two fields in various ways. This is just schematic. It's just to say that it's a bilinear with S derivatives, and it's totally symmetric and traceless operator, and it's conserved. And well, as you can see, just from the definition, is an operator which has dimension d minus 2 plus s. And that's just the dimension of a conserved spin S operator in a general CFT, as maybe you have learned last week, I'm not sure, in the lectures of Simone stuff. But in this case, because it's a free theory, you can just see directly that that's the dimension just by counting the dimension of this operator. Okay? So as I said, this is schematic. You can write down the explicit expressions for these operators and check that they are primary operators which are conserved. Just for completeness, let me write it down. Okay, so more explicitly, so first let me introduce a technique which is often useful when dealing with these higher spin operators, and will be also similar to how the higher spin fields are treated in the Vasiliev construction. So instead of actually working with this object which has S indices, it's convenient to work with an object which has no indices by contracting this spin S operator with some auxiliary vector, which I will call epsilon, which we can take to be null. Okay. So if we take this to be null, then this projection, this multiplication by epsilons automatically only selects the traceless part of this operator, which is what we want anyway. And the advantage of this is that we can then work with these operators which have no indices, and it's much nicer to work with these because it allows to basically forget about all subtractions of traces to make things traceless. And in this language, these spin S operators are simply given by the following expression. Where this AKS has some coefficients which are well known. These operators, for example, show up in QCD or in unequal force superior Mills. They are the twist 2 operators. Okay. So once you write it in this form, using these epsilon tensors, it's not too difficult to show that these operators are conserved. Now, going into the details of this will require some time, so I will just refer to you to this paper, actually of Joao and friends, where this formalism is used, and you can, well, reading the details there, you can try to show as an exercise that with this choice of coefficients, these operators are conserved. Okay? So you can imagine that once you do this, you can always recover the operator with the indices by just stripping off these epsilons and then subtracting all the traces. In practice, there is a very convenient procedure to do that, which involves applying some differential operator in this epsilon space, which you can find there. Okay, I don't have time to go into details of that now. Okay. And this formalism is also the most convenient formalism to use when you want to compute correlation functions of this object, because it allows you to not work with not being swamped by all these indices, but just to work with this much more convenient objects. Okay. But we will write down later probably some explicit expression for correlation functions of this. Okay. Okay, so notice that these operators that we have constructed, these conserved spin S operators, will, well, as usual, if we have a conserved current, it will imply that there are symmetries associated to it. So it means that this free scalar field theory has a large symmetry group, which is generated by the charges associated with these currents, and those are the higher spin symmetries. Right, so the schematic here. So conserved currents implies symmetries. And so, for example, using the presence of a conserved spin S current will mean that we can construct a charge of spin S minus 1, which is essentially by the usual way in which we construct conserved charges will be the integral of the current where one component is set to 0. Well, x. And then, so let me call this schematically QS. And one can then deduce what is the action of these symmetries on the field. And you can see, for example, that schematically these are higher derivatives symmetries of this type, where you have S minus 1 derivatives acting on phi. So here I'm being quick because later when we construct Vasiliev theory, we will have a better, more convenient formulation of what this symmetry group is. But what I wanted to say now is just that having these conserved currents imply that we have an infinitely many symmetries generated by these charges. And what is also clear is that if you look at the structure of this algebra, you can find that if you consider the commutators of two of these charges with spin greater than 2, then you will produce a charge of higher spin, even higher. And so that means that if there is one of these charges of spin greater than 2, you must have an infinite tower. For example, if you consider the commutator of 2 spin 4 charges, you get that this commutator will include a charge of spin 6. Now, of course, in this case, I'm constructing these operators explicitly in these free theories. We know that there are infinitely many of them. But you could proceed abstractly and assume that you have some CFT which has some spin 4 charge that acts in this way, and then you will find that it must have a spin 6 charge, and so on. Okay. And this basically is the CFT counterpart of the fact that in these higher spin theories, you have infinite towers of these massless higher spin fields. Once you have one, which is spin greater than 2, you must have infinitely many of them in order to have a consistent higher spin symmetry. Okay. All right. Yeah. It's the same. If you take the commutator of 2 spin 6, you will find a spin 8, but also spin 4. There is also charges of lower spin. By this, I don't mean that the commutator of 2 spin 4 gives just spin 6. It actually gives spin 6 and spin 2 as well. And the same way, if you take 2 spin 6, you'll get a spin 4. Again, we'll come back to this when we actually construct Vasiliev theory, in which this higher spin symmetry is realized in a slightly different way, but which makes this property more manifest. I want to flip the sign. Thank you. Thanks. Okay, so notice that all these operators that we have constructed are UN invariant. They are all invariant under this UN symmetry. Okay, so now, as I was already mentioning earlier, let me state for now, just by hand, that I want to study not the full CFT, but just the singlet sector of the CFT, just UN invariant operators. Okay, so now we already see that this tower of operators that we are constructed belong to the singlet sector because they are UN invariant. And so it's not difficult to see that at the level of bilinears, there is one additional operator, which is a scalar operator. Which I will denote as J0, which is, of course, just phi I. With it's a primary operator of this CFT. It's UN invariant, and it has dimension d minus 2, because the scalars have dimension d over 2 minus 1. So this operator also belongs to the singlet sector. And it's not difficult to see that at the level of bilinears, this is all that we have in the singlet sector, just this scalar plus this tower of higher spin operators. So J0 plus sum from 1 to infinity Js. These are all, let me now use this terminology and explain. These are all the single trace operators, or the single trace primaries in the UN singlet sector. So this terminology, single trace, is used by analogy with the example of joint type theories in which there is clear what single trace means. Here by single trace, I just mean that there is a single sum over this UN index. Okay, so these operators here, this J0 plus these towers, are the single trace operator of this theory. And you know from the lectures of Joao that single trace operators play a special role in ADS CFT because they are dual to single particle states in ADS, right? Okay, and objects which have more traces are dual to multi-particle states. So in this case of vector models, things which are multi-trace will be objects of this type. For example, this is a very simple double trace operator, just the product of two of the scalars. Or you can take more products, putting derivatives and so on. So this is a multi-trace operator. Its conformal dimension is the sum of the conformal dimensions of the two single trace operators. Now in this case it's exactly that. If in the theory we add interactions, then of course it will be the sum plus 1 over n corrections, right? If there are interactions. So objects of this kind will be dual to multi-particle states in ADS. So if we want to identify what is the spectrum of the ADS dual of this CFT, we can just focus on the single trace operators and try to match them with some single particle states, right? But the point of using vector models is that this single trace spectrum is extremely simple. It's just one scalar operator plus a tower of a higher spin operator, one for each spin. If instead I was discussing some matrix type theory, let's say a free matrix type theory, then there will still be a tower of higher spin conserved operators of the same type, trace of phi with s derivatives, but there will be many more single trace operators. So like trace, you can put as many phi's as you want. So the spectrum of single trace operator in a matrix type theory is much bigger. But the vector model has a very simple single trace spectrum. And now we can see that this single trace spectrum is in one-to-one correspondence with the spectrum that you find in the simplest higher spin theory that I wrote at the beginning in ADS4. CFT and ADS. So as I just said, we list here all the single trace operators and we try to match them to some field in ADS. And we can enumerate the single trace operators very simply. There is a scalar of dimension d minus 2 that must be dual to a bulk scalar field. Let me call it phi. Let me assume that I use Poincaré coordinates phi x z, where x is the, so here these currents are functions of x at the boundary, and in ADS we have one more coordinate, which is the z. And the usual ADS CFT dictionary tells you that the mass of the scalar field is related to the dimension of the dual operator by that formula. Did you already discuss this? And so if delta is d minus 2, that's m squared equal minus 2 d minus 2. I'm dropping now the ADS radius. I'm setting it to 1. Okay. So in ADS 4, which is d equal 3, this is m squared equal minus 2, which is the value I mentioned earlier. Now that value just comes out from Vasiliev equations because of the structure of the equations. That value comes out. But here we see that that value is precisely the value that you need in order for that field to be dual to this phi square operator in the CFT. And we can go on. We have a spin 1 conserved current. That must be dual. So the general fact in ADS CFT that conserved currents are dual to gauge fields in ADS. So a conserved current must be dual to a massless field here. So here we will have a spin 1 field. Let me call it phi mu, gauge field. Similarly, the spin 2, the stress tensor, of course, will be dual to the graviton. And it's clear how to generalize this to all spins. Now we know that in this CFT we have a tower of conserved currents of all spins. Now I'm being sloppy with indices here. Of course, this index here runs over one more coordinate, right? So let me call it phi m. So I will reserve mu. In this lecture, mu will be indices at the boundary, and then indices in the full ADS. Okay? And here we have spin S operator, which are conserved. And so that must be dual to massless higher spin fields of spin 3, 4, up to infinity, because we have infinitely many of this. Okay, so the spectrum, just following usual rules of ADS CFT, the spectrum of this CFT, restricted to its singlet sector, is in one-to-one correspondence with the spectrum of Vasiliev theory. Well, the simplest bosonic Vasiliev theory. Now, the fact that I impose the singlet sector constraint is important, because if I didn't do that, then I will be many more operators in this CFT, which are not singlet, and those do not have a counterpart there. So it's really the singlet sector of this vector model which is dual to the higher spin theory. Okay? And later we will see some explicit natural way in which you could impose this singlet sector constraint, which involves gauging this UN global symmetry that I had. Yes? Okay, so at the level of the spectrum, it doesn't show up. So let's see now where it shows up. It shows up in interactions. So this is just a matching of spectra. Now you can ask whether these fields are supposed to be interacting or not. In Vasiliev theory, these are highly interacting fields. But that's also now easy to understand from CFT point of view, and we will also tell us what is n in this correspondence. Okay. So how do we? So what is the thing that we naturally compute in ADS CFT? Of course, we don't just match spectra. That's too simple. So the thing that we usually compute, that ADS CFT is good at, is computing correlation functions of these single trace operators at the boundary from some ADS amplitude, right? So the picture that you have already seen is some Witten diagrams, right? So for example, if I want to compute the 3-point function of 3 of these operators in the CFT, how do I do that from ADS CFT dictionary? I will compute to leading order. I will have a process of this kind where so each of these insertion points here is one of these currents. And this is the field which is dual to it. So the massless field of spin S1, spin S2, spin S3. And let me call here a bulk coupling constant, G bulk. So G bulk is defined in such a way that the action is 1 over G bulk square integral of the Lagrangian. So in other words, in the usual convention of gravity, G bulk is like square root of Newton constant, right? So what usually in front of gravitational action is 1 over G Newton. So that's the coupling constant that appears there. And then there will be correction to this type, and so on, right? Similarly, you can compute 4-point function, and so on. But now, the point is that these 3-point functions of these operators, even though this is a free CFT, these 3-point functions are obviously non-zero. They are just you get some tensor structure times some coefficient, some non-zero coefficient. On the CFT side, you're just computing some very simple free field weak contractions. So a Feynman diagram of this type, where each of these points is one of these bilinears, and then you just have free propagators, right? So in the free CFT, it's very simple to compute these things. It's just some non-zero answer. So if you ever hope to reproduce that from an ADS calculation, it must be that these fields interact somewhere, right? If there was no interaction, I could not write down an amplitude like this. So these fields must be interacting. And it's easy to see that this coupling constant is related to n. So one, let's see, where can I go? So if we normalize these operators Js so that their two-point function does not scale with n of order 1, that means that I basically have to take this, put a factor of 1 over square root n in front, because the two-point function will involve a diagram which gives a factor of n. Right? So if we normalize this, which corresponds in the ADS side to normalizing these fluctuations so that their propagator is just order 1, doesn't scale with the coupling, then one can see that three-point function scales like 1 over square root of n. All right. So this means that this coupling constant in the bulk is 1 over square root n. Or in other words, Newton constant is 1 over n. Okay. So as usual in ADS CFT, we see that large n limit corresponds to weak coupling in the ADS. Right. So these interactions become small as n increases. The scaling in n is, again, different from what you're maybe more familiar with in Yang-Mills type theories, where Newton constant scales like 1 over n squared. Here, in this vector model, duality scales like n because of the different scaling with n of these bilinear operators when you consider their correlation functions. Okay. So to answer a previous question, n shows up in interactions. It basically, this bulk coupling constant is related to n. I've set the ADS radius to 1 here. More precisely, there is only one dimensionless parameter, which is the ratio of Planck length and the ADS length, where G Newton is 1 over Planck length square in ADS core. That's the only dimensionless parameter, and that dimensionless parameter maps to n on the CFT side. Okay? All right. What's the time? I have to till 5:15, 20, 5:20. Yeah, I think, okay. Yeah, I got confused with the time. You're right. Okay. So one particularly interesting example of a three-point function of this kind is the three-point function of the stress tensor. Right? That's one basic object that you could consider. And that will tell you what is the cubic coupling of the graviton in these models. Right? So this will be, let me call H the graviton fluctuation. Okay. So one natural question is, what is the cubic coupling of graviton in these models? Is it the same as the one that you get in Einstein gravity or not? It's easy to see that it's not. So in a general CFT, let's say in 3 dimensions, the three-point function of stress tensor is constrained just by conformal symmetry and conservation of this operator to be a linear combination of two terms. let me call them AB, T, 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 B plus AF, T, 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 F. So that's general in any CFT. Now, in this particular CFT that we are discussing now, of course, we will have AF is equal. Oh, I didn't say what are these. Okay. So, but B and F stands for boson and fermion. So these are linear combination of two structures, which are what you get if you take the 3-point function of stress tensor in a scalar theory and the 3-point function of stress tensor in a Dirac fermion theory. So any CFT will have a linear combination of these two terms. The one we are considering now is just a free scalar theory. So of course this term will not be there. There will just be this term. But people, well, several years ago, in early days of ADS-CFT, people computed what is this holographic 3-point function of stress tensor if you just use Einstein gravity. So if you use Einstein gravity in ADS, I'm not being careful about factors of 2 or definition of lambda here. Okay? So take this action and expand it to cubic order around the ADS background. You can read off what is that cubic coupling, and you can compute what is TTT, just following the rules of ADS-CFT. And what you find is a linear combination of these two terms. Okay, they are both there. It's actually, it agrees with a supersymmetric multiplet in 3 dimensions. So they're both bosons and fermions at the boundary. But so the important point is that if you just take this action, you're not going to get just the boson structure. You're going to get both. And you can change the relative coefficient between these two terms if you modify this action by higher derivative terms. Okay, so this gives both AB and AF non-zero using this. This calculation was done by Arutyunov and Frolov in 99. Okay. So you can balance the, well, you can change around these coefficients if you modify the Einstein action by including higher derivatives. So if you include higher derivatives, can achieve AF equal to 0 or AB equal to 0 if you suitably choose the higher derivative terms. So this argument basically tells us that whatever this dual theory is, it will have cubic coupling of the graviton, which does not agree with Einstein gravity, but it will require having higher derivative corrections on top of Einstein gravity, because we must have just AB and not AF. But that's precisely the structure that you get in Vasiliev theory. You do indeed get higher derivative interactions. And, this was checked explicitly, that if you use Vasiliev theory and try to compute this 3-point function, you do, in fact, get just the boson 3-point function. But I will discuss this quite a bit later. So that shows that, indeed, Vasiliev theory does have the correct higher derivative structure in order to achieve this. Okay. Any questions about this? Yes.
So you need the whole power of higher derivatives to be able to make
At the 3-point function level, actually, by field redefinition at 3-point function level, this can be just repackaged into just cubic coupling of Weil tensor. But the full tower will appear if you go to higher point functions. But okay, I don't want, it's a little bit technical. I don't want to go into that. Okay, I think let me just close by just one very simple remark. So far I was considering this UN, this complex scalar theory restricted to the UN singlet sector. Of course, you could also consider, as we said earlier, you could consider real scalar fields. Then this has some ON symmetry, where this is in the fundamental representation, and you can study the ON singlet sector of this theory. Now, things are very similar to what I discussed so far. The only difference is that in this case, in the ON singlet sector of this theory, the single trace spectrum is even smaller. There are no odd spin currents. So here there is only scalar plus S even. Okay, so that's because if you try to write down ON invariant operators of odd spin, they just vanish. For example, if you want to write down spin one current, which is ON invariant, that's of course 0 if these are real scalars, and the same is true for spin 3, 5, 7, and so on. So this theory must be then dual to a different higher spin theory in which there are no odd spin higher spin gauge fields, right? But that's actually that theory actually exists. It's just dual to what is called minimal Bosonic Vasiliev theory. So it turns out that there is a consistent truncation of that bosonic theory with all integer spins. There is a consistent truncation of it in which you drop all the odd spin fields. Okay, and that consistent truncation has a natural counterpart here in this ON singlet sector of this CFT. Okay, there is no consistent truncation where you drop even spins. Okay, so this is the only consistent truncation of that theory. You drop all the odd spins. In particular, the graviton still must be there, of course, because you always have a stress tensor in these theories. So this is called minimal because there is no smaller higher spin theory in ADS. Okay, just have all the even spins. And when we introduce the Vasiliev theory later, we will come back to this minimal truncation. But it's something simple. It's just that you can impose some condition on your fields so that all the odd spin are dropped and that truncation is consistent. Okay. So I think I'm out of time. So tomorrow I'll go on with CFT, trying to discuss interacting versions of these vector models and what are they due to. And maybe at the end of the lecture, we'll start introducing the higher spin equations, hopefully. Okay, so yeah, so see you tomorrow. Questions? Yes?
Is it obvious that these JS are the only things in the singlet sector? I mean, because they have two phi's for these particular derivatives.
Right. Well, maybe it's not obvious, but you can show it. You just write down the most general bilinear, and you show that there is only one primary operator for each spin. Yeah.
In what sense is Vasiliev theory consistent? Because you don't know how to quantize it. Why do you call it consistent?
Well, it's consistent in the sense that you have a set of nonlinear equations of motion which are gauge invariant, and they give, if you study perturbatively, they give unitary propagation of fields. And, well, whether it's consistent at the quantum level, it's an open question, but it's believed to be true. And of course, if we believe this ADS-CFT correspondence, then it's very natural that these theories are fully consistent because they are dual to something very simple, which is just a free scalar CFT, well, restricted to the singlet sector. So from CFT point of view, it's natural that these theories should be consistent. from Vasiliev point of view, they are consistent in the sense that they are gauge invariant under nonlinear gauge symmetries, and they are consistent as classical equations of motion. No, that's non-trivial. So that's something that you need to check. It's just from a point of view of Witten diagram expansion is not trivial that there are no anomalous dimensions. Well, there is higher spin symmetry argument because the higher spin symmetry. I'm not aware of it. Just at the level of the Witten diagram. I think it's non-trivial to actually see it. So anomalous dimensions will be produced by diagrams of this type, loop diagrams of this type. Okay. So in the interacting versions of these dualities, such diagrams are expected to be non-zero because there are 1/n corrections to the dimensions, as we discussed tomorrow. So there are two versions of these higher spin theories, which are, well, dual to either this free CFT, where there are no anomalous dimensions, or some interacting CFT, where then there are anomalous dimensions. So we'll discuss more tomorrow. It depends on what is, well, in the simplest version, it depends on what is the precise fields that run here. You have a choice of how you quantize the scalar field, for example, what is the boundary condition that you choose, and that makes the diagram vanishing or non-vanishing. Well, nobody has shown that it vanishes for the choice of free CFT, but what you can show is that if it vanishes for the theory dual to free CFT, then it will not vanish for the other one, and it will produce an anomalous dimension. But we will have to discuss this in more detail tomorrow. Anything else? Okay. In three dimensions.
I'm saying that in the sense of the TT. Or is there anything universal
They're not determined by. Yes. I mean, you have freedom of this improvement once you present this basis. Maybe I thought this was Scalar operator. Spin fixed up to a sum of finitely many stuff. In the case of CFT in freedom, but it depends. If you increase the dimension, there could be more.
Truncation of the CFT.
Yeah.
The OPE of the singlet, it is sort of operated with the
yeah.
chemistry.
Yes.
It's consistent.